The moon is covered in treasure, oxygen locked inside rock, water frozen in eternal shadow, metals, rare isotopes, and enough raw material to build a civilization. Headlines say we just need to go dig it up, but here is what those headlines leave out. Every shovel of lunar soil is made of glass shards sharper than surgical blades. Every machine you send will grind itself to death in months. Every drop of water you want sits in craters so cold that steel becomes as brittle as ceramic. And every piece of equipment you bring to fix the first machine needs its own power supply, its own thermal protection, and its own defense against the same dust that destroyed the original. Mining the moon is not one hard problem. It is a chain of hard problems, and every link makes the next one worse. If you want to understand why the moon's riches might be the hardest treasure humanity has ever tried to reach, go ahead and hit that like button and subscribe. Now, settle in, get yourself comfortable. Let's begin. The moon is the closest world to Earth, and for most of human history, that was the only interesting thing about it. A grey companion hanging in the sky, close enough to see craters with a backyard telescope, far enough away that reaching it nearly bankrupted the most powerful nation on the planet. 6 Apollo crews walked on its surface between 1969 and 1972. They collected rocks, planted flags, drove a car, hit a golf ball, and came home. And after Apollo 17 lifted off from the Taurus-Littrow Valley in December of 1972, nobody went back. For 50 years, the moon sat in the public imagination as a place we had already visited. A trophy. A been there, done, that destination with grey dirt and no atmosphere, and nothing particularly worth returning for. Then the data started arriving. In 2008, India's Chandrayaan-1 spacecraft entered lunar orbit, carrying a set of instruments designed to scan the surface in ways the Apollo missions never could. One of those instruments, a NASA-built mineralogy mapper, detected something that changed the entire conversation about the moon. It found signatures of water molecules and hydroxyl compounds spread across the lunar surface. Not oceans, not rivers, not even puddles, but molecular water embedded in the upper layers of regolith, present in quantities that were small per cubic meter, but enormous when spread across the surface of an entire world. The discovery was not water in the way most people picture it. It was water molecules trapped in glass beads and mineral grains, baked into the soil by billions of years of solar wind bombardment. Hydrogen ions from the sun had been slamming into oxygen-rich minerals on the lunar surface for eons, creating hydroxyl groups and, in some cases, actual water molecules locked inside the crystal structure of the rock itself. The following year, NASA deliberately crashed a spent rocket stage into a permanently shadowed crater near the lunar South Pole as part of a mission called L-Cross. The impact threw up a plume of debris, and instruments aboard a trailing spacecraft analysed what came out of the darkness. The answer was water ice. Real, solid water ice sitting in a crater that had not seen sunlight in billions of years. The permanently shadowed regions near the moon's poles are among the coldest places in the entire solar system. Temperatures inside these craters drop to roughly -220 degrees Celsius, cold enough that any water molecule drifting across the surface and falling into that shadow stays frozen essentially forever. Over billions of years, comets, asteroids, and solar wind interactions deposited water in these cold traps grain by grain, molecule by molecule, building up reservoirs of ice mixed into the regolith at concentrations estimated between 2 and 10% by weight. Suddenly, the moon was not just a dead rock, it was a warehouse, and water was only the beginning of the inventory. Lunar regolith, the loose, rocky soil covering the entire surface to depths of several meters in most places, is approximately 40% oxygen by weight. That oxygen is not floating around as breathable gas. It is chemically bonded to silicon, iron, aluminum, calcium, magnesium, and titanium in mineral compounds. Silicon dioxide, aluminum oxide, iron oxide, calcium oxide. The regolith is essentially a mix of metal oxides, which means it is simultaneously a source of oxygen and a source of metals if you can find a way to break those chemical bonds. The metals themselves read like a list of industrial essentials: iron for structural components, aluminum for lightweight construction, titanium for high-strength, corrosion-resistant applications, calcium for potential use in cement-like binders, silicon for electronics and solar cells. These are not exotic trace elements. They are bulk constituents of the soil, present in percentages, not parts per million. Every square meter of the lunar surface is blanketed in material that contains the chemical building blocks of an industrial civilization. Then there is helium-3. The moon's surface has been bathed in solar wind for billions of years with no magnetic field and no atmosphere to deflect it. Among the particles embedded in the regolith by this bombardment is helium-3, a light isotope that is vanishingly rare on Earth, but theoretically valuable as fuel for a future generation of nuclear fusion reactors. Helium-3 fusion, if it can ever be made practical, would produce enormous energy with minimal radioactive waste. The concentrations in lunar soil are tiny, roughly 4 to 15 parts per billion, but the sheer volume of accessible regolith means the total supply could be significant if anyone could extract it economically. And this is where the story most people hear comes to a stop. The moon has water, the moon has oxygen, the moon has metals, the moon has a rare fusion fuel. The narrative leaps directly from inventory to destiny. Headlines: Announce the lunar economy. Startups pitch investors on trillion-dollar resource plays. Animated concept videos show rovers scooping soil and processing plants humming in the shadow of a crater rim. The assumption is seductive and intuitive. The hard part is getting to the moon. Once you are there, the resources are just sitting in the dirt. Scoop them up, process them, build things, refuel rockets, sustain a base. Launch a new era of human expansion into the solar system. The assumption is also wrong. Not wrong about what exists on the moon. The resources are confirmed. Orbital instruments, impact experiments, and sample analysis have verified the presence of water ice, metal oxides, and embedded volatiles. What is wrong is the invisible leap between identifying a resource and turning it into something usable. That leap, on the moon, is not a step. It is a chasm, and almost nothing about the popular vision of lunar mining survives the crossing. To understand why, you have to start with what mining actually means. Not the simplified cartoon version where a machine digs a hole and useful material comes out. Real mining, on Earth, is a chain of interconnected operations. You survey a site, you remove overburden, you excavate the ore, you crush it, sort it, wash it, heat it, chemically process it, refine it, transport it, and store the product. Every step in that chain depends on the steps before it and enables the steps after it. And every step depends on a surrounding ecosystem of support: power plants, roads, water supplies, spare parts, maintenance crews, fuel deliveries, waste disposal, communication networks, weather forecasting, legal frameworks, supply chains stretching across continents. On Earth, this support ecosystem is so ubiquitous that it becomes invisible. You do not think about the fact that your mining truck can drive on a road that someone else built, or that a broken hydraulic line can be replaced by a part shipped overnight from a warehouse in another state, or that the diesel fuel powering the excavator arrived by train from a refinery hundreds of miles away. You do not think about the atmosphere providing convective cooling to your engine, or gravity providing traction to your wheels, or the fact that your workers can breathe without carrying their own oxygen supply. All of these things are free on Earth. They are the background conditions of terrestrial industry. They are so fundamental that removing any one of them would cripple mining operations, and on the moon, every single one of them is missing. But saying they are free understates what the Earth actually provides. Consider just water. A single large copper mine on Earth might consume 150 to 200 million litres of water per day. That water suppresses dust on haul roads. It cools drilling equipment. It carries crushed ore through flotation cells where valuable minerals are separated from waste. It washes processing equipment. It sustains the workers who maintain the machines. And when that water is contaminated by the process, it flows into tailings ponds where natural evaporation and microbial activity begin breaking down the pollutants. The mine does not manufacture this water. It does not launch it from another continent. It draws it from rivers, wells, and rainfall that exist as permanent features of the terrestrial environment. Water is so abundant and so cheap on Earth that mining engineers treat it as a utility, something that arrives through a pipe and shows up as a minor line item on the operational budget. On the Moon, water is the prize, not the tool. Every drop of it must be extracted from frozen regolith at enormous energy cost before it can be used for anything, and the idea of spending scarce lunar water to suppress dust or cool a drill bit is economically and logistically absurd. The resource you are mining cannot simultaneously be the resource you consume to mine it, not at the beginning, not until production vastly exceeds demand, which is a milestone that lies decades beyond the first operational plant. Now consider gravity. On Earth, gravity does far more for mining than simply keeping equipment on the ground. It is the engine behind almost every separation process in mineral beneficiation. When you crush ore and drop the fragments into a water bath, heavy mineral grains sink faster than light waste rock. This is gravity separation, and it is one of the oldest and cheapest ways to concentrate valuable material. When you pour crushed ore onto a vibrating screen, gravity pulls smaller particles through the mesh, while larger ones roll off the end. When you load processed material into a hopper, gravity feeds it downward into the next stage of the process. Granular flow, the way powdered or crushed material moves through chutes, pipes, and storage vessels, is governed by gravity. Every hopper, every conveyor transition, every settling tank in a terrestrial processing plant is designed around the assumption that gravity will pull material downward at 9.8 meters per second squared. On the Moon, gravity pulls at 1.6 meters per second squared. Material settles 6 times more slowly. Particles that would fall cleanly through a screen on Earth linger and clog. Hoppers designed for terrestrial granular flow rates jam because material does not slide as aggressively down inclined surfaces. Density separation in liquid media, if any liquid could be maintained in vacuum at all, becomes 6 times less effective because the differential settling velocity between heavy and light particles shrinks proportionally. Every piece of processing equipment designed using terrestrial intuition about how granular material behaves must be fundamentally redesigned for 1/6 gravity, and almost no testing of mineral processing in sustained reduced gravity has ever been performed, because the only way to simulate lunar gravity for more than a few seconds is in a drop tower or a parabolic aircraft flight, neither of which lasts long enough to test continuous industrial processes. Then there is atmospheric pressure, something so constant on Earth that most people never think about it as an industrial resource. But atmospheric pressure is what keeps lubricating oils in liquid form. It is what allows pressurized hydraulic systems to function without boiling. It is what enables the air-cooled radiators on every diesel engine, every generator, every piece of electrical equipment in a terrestrial mine. It is what keeps fine dust from behaving like a charged, adhesive weapon. On Earth, atmospheric pressure pushes back against the tendency of volatile fluids to evaporate. It provides a dense medium through which heat can be convected away from hot surfaces. It moderates the electrostatic behavior of fine particles by providing a conductive path for charge dissipation. Humid air in particular bleeds away static charge, which is why dust problems on Earth are worst in dry environments and minimal in wet ones. The Moon has no atmosphere, no humidity, no pressure, and no convective medium. Every function that air performs silently and invisibly in a terrestrial mine must be replaced by an engineered system on the Moon, and every one of those engineered systems adds mass, complexity, power demand, and failure modes. There is no atmosphere to provide convective cooling or to protect machinery from radiation. There is no magnetic field to shield electronics from charged particles. There is no weather to erode sharp rock fragments into manageable soil. There are no roads, no supply chains, no warehouses, no maintenance crews, no fuel deliveries, no water for washing or cooling, no spare parts closer than 380,000 kilometers away, and no possibility of rapid resupply when something breaks. Gravity is 1/6 of Earth's, which sounds like it should make digging easier, and in some narrow sense it does reduce the energy needed to lift a scoop of soil. But reduced gravity also means reduced traction for wheels and tracks, reduced settling of material in hoppers and processing vessels, and altered behavior of every fluid and granular flow that industrial processes depend on. Dust does not settle the way it does on Earth. Excavated material does not pour the way it does on Earth. Nothing behaves the way decades of terrestrial engineering experience has trained us to expect, and this is before you even consider the regolith itself. Lunar regolith is not soil. It is the accumulated debris of 4.5 billion years of meteorite bombardment in a vacuum. Every particle has been shattered, melted, reshattered, and welded together by the energy of countless impacts. The result is a material unlike anything found naturally on Earth. The grains are jagged, angular, and sharp because there is no wind, no water, no biological activity to round them off. Many particles are coated in or composed of agglutinates, tiny clumps of mineral fragments welded together by impact glass. These agglutinates are even more abrasive than the raw rock fragments because their surfaces are irregular and their glass coatings are hard and brittle. The finest fraction of the regolith, the dust, is electrostatically charged by exposure to solar ultraviolet radiation and the solar wind. This charge makes the dust cling to every surface it contacts. It sticks to metal, to glass, to fabric, to optical lenses, to thermal radiators, to solar panels. It does not brush off easily because the electrostatic attraction holds it in place. And when it does move, it abrades whatever it touches, scratching glass, grinding into seals, embedding itself in the gaps between moving parts. NASA learned this during Apollo. Astronauts on every surface mission reported problems with dust. It clogged equipment, it scratched visors, it coated instruments, it infiltrated suit joints and made them stiff. Harrison Schmitt, the geologist who walked on the moon during Apollo 17, reported symptoms resembling hay fever after inhaling lunar dust inside the cabin. The dust was so fine and so pervasive that it penetrated the spacecraft's environmental systems. And the Apollo missions lasted only a few days each. The astronauts were on the surface for hours, not weeks or months or years. They were exploring, not mining. They were picking up rocks, not excavating thousands of tons of regolith. The dust problems they encountered were a whisper of what sustained industrial operations would face. This whisper should have been a warning. In many ways it was. Engineers and scientists who study lunar surface operations have spent decades documenting exactly how hostile regolith is to mechanical systems. NASA formally identified 9 distinct engineering threats posed by lunar dust, ranging from seal failure and equipment clogging to thermal radiator degradation and progressive abrasion of every exposed surface. Each of these threats is individually serious. Together, they form an environment that actively degrades every piece of equipment placed on the lunar surface from the moment it begins operating. Yet somehow, the public conversation about mining the moon rarely mentions any of this. It skips from resource maps to revenue projections as if the regolith were cooperative topsoil waiting to be shoveled into a hopper. This gap between reality and perception is not accidental. It exists because the difficulties of lunar mining are not dramatic in the way that rocket explosions or deep space radiation are dramatic. They are grinding, iterative, systemic difficulties. A bearing wearing out 3 times faster than expected. A seal failing after 2 thermal cycles instead of 20. A solar panel losing 15% of its output in the first week because of dust accumulation. A drill bit dulling in hours instead of months. None of these sound catastrophic in isolation. But in a place where every replacement part must be launched from Earth at a cost of tens of thousands of dollars per kilogram, where every repair requires either a human in a spacesuit or a robot that itself needs maintenance, where every delay in one system cascades through every connected system, the cumulative effect is devastating. This is why NASA's Viper rover serves as such a revealing case study, even though it never reached the lunar surface. Viper, which stood for Volatiles Investigating Polar Exploration Rover, was designed specifically to prospect for water ice in the permanently shadowed regions near the South Pole. It was not a mining machine. It was a scout. Its job was to drive into shadowed craters, drill into the regolith to a depth of about 1 meter, and analyze what it found. It carried 4 instruments for detecting and characterizing water ice and other volatiles. Its mission would have lasted approximately 100 days. This was supposed to be the modest first step, the reconnaissance that would tell us whether lunar ice mining was even worth attempting at scale. The rover was announced in 2019. Development began at NASA's Johnson Space Center. By 2021, the project had been confirmed, with a congressional budget of $433.5 million and a planned launch date in late 2023, aboard Astrobotic's Griffin lander as part of NASA's Commercial Lunar Payload Services program, known as CLPS. Then the delays began. Supply chain disruptions during the pandemic slowed deliveries of critical components. Testing revealed issues that needed resolution. The launch slipped from 2023 to 2024. Costs rose to $505 million. The launch slipped again to September of 2025. Costs climbed to $609.6 million. In July of 2024, NASA cancelled the mission entirely. $600 million for a rover that never left Earth, for a mission that was not even attempting to mine anything, just to determine whether mining might someday be feasible. The rover's hardware was complete, its instruments worked, its software was ready. But the costs of delay, the complexity of building a machine that could survive and operate in the lunar polar environment, and the cascading budget pressure on other lunar missions made continuation impossible. NASA officials stated that cancelling Viper would save at least $84 million and potentially much more if the launch window was missed again, which would have required waiting 9 to 12 months for the right lighting conditions at the South Pole to return. The Viper cancellation is not a story about bureaucratic failure or bad management. It is a story about how difficult it is to build even a small robotic explorer for the lunar surface, let alone an industrial mining operation. The rover weighed approximately 500 kilograms. A single machine with no processing plant, no transport network, no maintenance infrastructure, and it cost more than $500 million before it was cancelled. The engineering challenges of surviving the lunar environment, of operating in shadowed craters at cryogenic temperatures, of drilling through abrasive regolith in vacuum, of managing thermal extremes that would destroy unprotected electronics, drove the complexity and cost far beyond initial projections. Meanwhile, Artemis II launched successfully in April of 2026, sending 4 astronauts around the Moon on a 10-day test flight. The first crewed lunar landing since Apollo is now targeted for 2028 with Artemis IV. These missions represent extraordinary achievements in human spaceflight, but they are transportation achievements. Getting people to the Moon and back, the challenge of what those people would actually do on the surface to build a sustainable industrial presence, remains almost entirely unsolved. There was one small bright spot in early 2025. In March, Firefly Aerospace's Blue Ghost Mission 1 lander touched down at Mare Crisium, carrying 10 payloads including 2 technologies developed by Honeybee Robotics. PlanetVac, a pneumatic regolith collection system, used compressed gas to kick up lunar soil and capture it within seconds, far faster than traditional mechanical scooping. Lister, a thermal probe, was designed to measure the heat flow beneath the surface. These were technology demonstrations, brief tests lasting hours, and PlanetVac showed genuine promise for rapid surface sampling. But a sampler that works for a few minutes on the surface is not the same as an excavation system that operates continuously for months. The gap between demonstration and industry remains enormous. The honest picture of where we stand today is this. We know, with reasonable confidence, that the Moon contains resources worth pursuing. Orbital measurements and limited surface experiments have confirmed water ice in polar cold traps, oxygen and metals in regolith across the entire surface, and trace amounts of helium-3 embedded by solar wind. What we do not know, because we have never tested it, is whether any of these resources can be extracted, processed, and used at meaningful scale in the actual lunar environment. We have never operated a drill on the Moon for more than a few minutes. We have never run a chemical processing reactor on the lunar surface. We have never maintained a machine through even a single complete thermal cycle, from lunar day to lunar night and back. We have never moved bulk regolith from one location to another over any significant distance. We have never produced a single usable gram of water, oxygen, or metal from lunar soil on the Moon itself. Every ambitious plan for lunar mining, from startup pitch decks to National Space Agency roadmaps, is built on the assumption that these things can be made to work. That assumption may ultimately prove correct. Humans are extraordinarily good at solving engineering problems when the motivation and resources are sufficient. But the assumption is untested, and the lunar environment has a way of punishing assumptions. To see why, you have to look at the specific mechanisms that make lunar operations so much harder than they appear on paper. The resource maps are real, the technology concepts are plausible, but between the map and the factory lies an environment that attacks every component of every system that anyone has ever proposed to place on its surface. That environment starts with the ground itself, with a substance so hostile to mechanical systems that engineers have compared working in it to operating inside a sandblaster that never turns off. What that substance does to machinery, and why it makes every subsequent step of the mining chain exponentially harder, is where this story truly begins. Pick up a handful of dirt in your backyard. Feel it between your fingers. It crumbles. The grains are soft, rounded, worn smooth by millions of years of wind, water, frost, and biological activity. Earthworms have passed it through their bodies. Rain has tumbled it down hillsides. Rivers have rolled it against other grains for centuries, knocking off sharp edges, polishing surfaces, reducing every particle to a blunt little pebble of mineral matter. This is what soil means to every human being who has ever planted a garden, walked on a beach, or kicked dust off a trail. Soil is familiar. Soil is manageable. Soil is what we imagine when someone says the word dirt. Lunar regolith is not dirt. It has never been touched by wind, because the moon has no atmosphere. It has never been tumbled by water, because the moon has no liquid water. It has never been digested by organisms, because the moon has no life. It has never been chemically weathered by acid rain or oxygen exposure. For 4.5 billion years, the only forces acting on the lunar surface have been vacuum, radiation, micrometeorite bombardment, and the relentless flux of charged particles streaming from the sun. Every grain of regolith on the moon was created by violence and preserved by stillness. Impacts shattered bedrock into fragments. Smaller impacts shattered those fragments into smaller pieces. The tiniest impacts, millions of them per square centimetre over billions of years, pulverized the surface layer into a fine powder of broken glass, mineral shards, and agglutinates. And because there is no atmosphere to carry those particles, no water to smooth them, and no biological or chemical process to soften their edges, every single grain remains exactly as sharp as the moment it was created. This is the first fact that separates lunar mining from terrestrial mining in a way that most people never grasp. The material you are trying to excavate is not passive. It is actively hostile to the equipment doing the excavating. Under an electron microscope, lunar dust particles look nothing like Earth sand. Earth sand grains are rounded, sometimes nearly spherical, shaped by eons of abrasion against other grains. Lunar dust particles are angular, fractured, jagged. Many have edges sharper than broken glass because they are broken glass. The impacts that created them generated enough heat to melt rock into tiny droplets that cooled instantly in vacuum, forming glassy beads and splashes. These glass fragments shattered on subsequent impacts, creating shards with edges measured in fractions of a micrometer. Some particles are hooks and needles of glass thinner than a human red blood cell. Mixed in with these raw fragments are agglutinates, and these are even worse. Agglutinates form when micrometeorite impacts partially melt the soil and weld together a random collection of mineral grains, glass shards, and metallic iron droplets into an irregular clump. The resulting particle is like a tiny piece of concrete studded with broken glass and metal filings. Its surface is rough, its shape is chaotic, and its hardness is extreme. Agglutinates make up a significant fraction of mature lunar soil, sometimes 30 to 60% of the finest grain sizes. They are the most abrasive component of the regolith because their surfaces combine the hardness of glass with the irregularity of a natural composite material. The size distribution of this material compounds the problem. Lunar regolith spans a wide range of particle sizes, from grains visible to the naked eye down to dust particles smaller than 1 micrometer. The finest fraction, often called lunar fines, is the most dangerous to equipment. These sub-micrometer particles are small enough to penetrate seals, infiltrate bearings, coat optical surfaces, and embed themselves in the microscopic gaps between moving components. On Earth, fine industrial dust is managed through filtration, lubrication, and sealed housings. On the Moon, the electrostatic properties of the dust make every one of those strategies dramatically harder. This is the second critical fact. Lunar dust is not just sharp, it is sticky. The Moon has no atmosphere and no global magnetic field. The surface is directly exposed to solar ultraviolet radiation and the solar wind, a stream of energetic protons and electrons flowing outward from the Sun. This radiation strips electrons from the surfaces of exposed particles through a process called photoemission. On the sunlit side of the Moon, dust grains accumulate a net positive charge. On the shadowed side, where electrons from the solar wind accumulate without being knocked away by ultraviolet light, particles become negatively charged. In both cases, the result is the same. Every grain of lunar dust carries an electrostatic charge. This charge makes the dust behave in ways that violate the intuitions of anyone accustomed to working with powdered materials on Earth. Charged particles cling to surfaces through electrostatic attraction, not just gravity. They adhere to metal, glass, fabric, ceramic, plastic, and painted surfaces with a tenacity that mechanical brushing cannot fully overcome. Apollo astronauts tried brushing dust off their suits and equipment. It came off partially, but a fine residue always remained, bonded to the surface by electrostatic forces and by the mechanical interlocking of jagged particle edges with surface irregularities. The harder you brush, the more you drive the sharpest particles into the material, creating scratches that give future dust particles even more places to lodge. On Earth, you can wash equipment, blow it off with compressed air, or use electrostatic discharge to neutralize clinging particles. On the Moon, there is no water for washing. There is no atmosphere for compressed air. And the electrostatic environment is continuously regenerated by solar radiation, meaning that any surface you clean will begin accumulating charged dust again immediately upon re-exposure. Cleaning is not a solution on the Moon. It is a temporary delay in a process that never stops. Now imagine operating a mining excavator in this material. Every component exposed to the regolith, every bucket edge, every hinge, every hydraulic cylinder, every wheel or track surface, every seal on every joint, is being abraded by particles harder and sharper than anything a terrestrial machine encounters outside of specialized grinding operations. The abrasion is not occasional, it is continuous. Every motion of the machine grinds dust into every contact surface. The teeth of an excavator bucket do not just scoop regolith, they drag across particles that scratch and gouge the metal with every pass. Bearings designed to rotate smoothly for thousands of hours on Earth begin degrading within days or weeks as dust infiltrates past seals and grinds between rolling elements. Gears mesh with fine, abrasive powder trapped between their teeth, accelerating wear rates by orders of magnitude compared to lubricated terrestrial operation. And lubrication itself becomes a problem. Conventional liquid lubricants evaporate in the lunar vacuum. Without atmospheric pressure to keep them in liquid phase, oils and greases sublimate, leaving dry contact surfaces that are instantly invaded by fine dust. Solid lubricants like molybdenum disulfide or certain polymer coatings can work in vacuum, but they wear out faster under abrasive loading and cannot be reapplied without maintenance intervention. The machine is being ground to death from the inside, and the most basic terrestrial defense against mechanical wear, a film of oil, does not survive the environment. This is not speculation. It is confirmed engineering analysis supported by decades of laboratory testing with lunar simulant materials, by direct experience during the Apollo missions, and by recent research presented at events like ESA's Planetary Dust Contamination Workshop in 2025. That workshop brought together researchers from across Europe who are actively testing how lunar-grade abrasive particles destroy seals, degrade solar cells, reduce the thermal performance of radiators, and infiltrate the joints of robotic arms. Their findings are consistent and sobering. The degradation rates are high, the mitigation options are limited, and the problem gets worse, not better, the longer equipment operates on the surface. The Apollo missions provide the closest thing we have to field data, and even though those missions were brief and focused on exploration rather than industry, the dust problems they encountered were severe. Eugene Cernan, commander of Apollo 17, described lunar dust as one of the most serious obstacles to sustained operations on the Moon. He reported that dust coated everything within hours of beginning surface activities. It obscured markings on equipment. It reduced the grip on tools. It accumulated on thermal radiator surfaces, reducing their ability to shed heat. It coated the lenses of cameras and the reflective surfaces of scientific instruments. On Apollo 16, astronaut Charlie Duke noted that dust had so thoroughly coated the rover's battery covers that the thermal management system was compromised, causing battery temperatures to rise above design limits during the final traverse. The AL-SEP scientific instrument packages left on the surface by multiple Apollo missions experienced progressive degradation from dust accumulation. Thermal control surfaces lost their designed reflective properties as dust coatings altered their ability to absorb and emit radiation. Some instruments showed measurable performance degradation within the first lunar day of operation. And these were stationary scientific packages with no moving parts exposed to the regolith. Mining equipment would face incomparably greater exposure because the act of digging and moving soil is the act of maximizing contact between machinery and the abrasive material that destroys it. Here is where the logic becomes circular, and this circularity is one of the most underappreciated aspects of the entire lunar mining problem. Mining requires excavation. Excavation disturbs regolith. Disturbing regolith liberates the finest, most abrasive, most electrostatically active dust particles from the surface. Those particles coat and infiltrate the very machine that disturbed them. In reduced lunar gravity, 1/6 of Earth's disturbed particles follow longer ballistic trajectories than they would on Earth. A grain launched upward by a bucket strike travels 6 times higher and 6 times farther before landing. Fine particles, given an initial velocity by excavation, can travel hundreds of meters across the surface before settling, coating equipment, solar panels, and habitat surfaces far from the dig site. Electrostatic levitation can loft the smallest particles, those below about 20 micrometers, even without mechanical disturbance, meaning that the ambient environment near any active mining operation would be a persistent haze of razor-sharp, electrostatically charged particulate matter. And unlike dust on Earth, this ejected material encounters nothing to slow it down. There is no air resistance. A particle launched sideways by the scrape of a bucket against rock follows a clean ballistic arc, decelerating only under the moon's feeble gravity until it lands somewhere else. On Earth, the same particle would hit a wall of air molecules within centimeters of being launched and lose most of its velocity almost instantly. A terrestrial dust cloud rises, billows, and settles within meters of its source, because atmosphere absorbs kinetic energy and friction, with air molecules drags particles down. On the moon, there is no such friction. Dust launched at modest velocities during excavation can arc dozens or even hundreds of meters downrange before touching the surface again. At an active mining site where excavators are repeatedly striking, scooping, and dumping regolith, the cumulative effect is a constant rain of fine abrasive particles landing across the entire operational area. Your processing plant receives a thin deposit of fresh dust with every excavation cycle, even if it sits 100 meters away from the dig face. Your solar panels accumulate abrasive coating, even if they are positioned on a ridge above the mining zone. Your habitat modules, your communication antennas, your stored spare parts, everything within the operational radius of an active excavation site is being slowly sandblasted by the mining operation itself. This has profound implications for site layout that have no parallel in terrestrial mining. On Earth, you can separate functions spatially. The processing plant sits upwind from the dig site. The maintenance shop sits across a paved yard. Workers park their vehicles in a clean zone and walk to the dusty area. Air carries contamination in predictable directions, and you design your layout to keep sensitive equipment upwind or inside filtered buildings. On the moon, there is no wind, which sounds like an advantage until you realize that it also means there is no preferential direction for dust transport. Ejected particles travel equally in all directions along ballistic arcs. You cannot put your processing facility upwind because there is no wind. You cannot build a wall to block dust because the particles arc over any wall that is shorter than their ballistic peak. You cannot enclose the mining site because enclosing an area large enough for active excavation would require a structure of impractical size, and the interior of that structure would rapidly fill with suspended dust that has no atmospheric drag to bring it down. The only reliable way to protect sensitive equipment from excavation-generated dust would be to place it far enough from the dig site that ballistic trajectories cannot reach it, which for vigorous excavation activity could mean separating functions by hundreds of meters or more. But greater separation means longer transport distances for excavated material, which means more energy spent on transport, more wear on transport vehicles, and more operational complexity. You are forced to choose between collocating your systems and accepting severe dust contamination, or separating your systems and paying a punishing transport penalty. There is no good option. There is only a choice between two different burdens. On Earth, mining operations generate dust too, and it is a recognized health and equipment hazard. But on Earth, you suppress dust with water sprays. You filter air through industrial scrubbers. You seal equipment housings and pressurize them to keep dust out. You replace worn parts from a warehouse down the road. You shut down operations during dust storms and resume when conditions clear. None of these options exist on the Moon in their terrestrial form. Every litre of water on the Moon has been extracted at enormous cost, not piped from a river. Air filtration requires atmosphere. Equipment seals are the components most vulnerable to dust infiltration. Replacement parts are 380,000 kilometers away, and the dust does not clear. There are no storms on the Moon, but there is also no rain, no settling atmosphere, no mechanism to remove dust from surfaces once it arrives. Every grain that lands on a solar panel stays there unless physically removed. Every particle that infiltrates a seal stays there unless the seal is replaced. The environment does not recover, it only accumulates damage. NASA formalized this understanding into a list of 9 specific engineering challenges caused by lunar dust, and that list deserves attention because it reveals how comprehensively the problem affects every aspect of surface operations. The first challenge is obscured vision. Dust coats camera lenses, helmet visors, and optical sensors, reducing visibility for both humans and robots. The second is equipment clogging. Dust accumulates in vents, filters, valves, and any opening designed for airflow or fluid flow. The third is coated surfaces. Every external surface gradually loses its designed optical and thermal properties as dust coverage increases. The fourth is loss of traction. Dust on wheels, tracks, or walking surfaces reduces friction, making locomotion unreliable on slopes or uneven terrain. The fifth is dust inhalation. For any crewed mission, fine respirable dust entering habitats poses a direct health hazard, as the particles are small enough to penetrate deep into lung tissue and sharp enough to cause mechanical damage to cells. The sixth is degradation of thermal radiators. Equipment on the Moon sheds waste heat through radiation, and dust coating on radiator surfaces reduces emissivity, causing equipment to overheat. The seventh is instrument contamination. Scientific sensors and navigation instruments produce false or degraded readings when their surfaces are coated in dust. The eighth is seal failure. Pressurized modules, spacesuits, sample containers, and any system requiring a gas-tight seal is vulnerable to dust infiltrating the sealing interface and preventing closure. The ninth is abrasion. Every exposed surface, whether moving or stationary, suffers progressive material removal from contact with abrasive dust. 9 threats. Every one of them confirmed by Apollo experience or laboratory testing, every one of them getting worse with longer exposure time, and every one of them affecting the mining equipment that would generate the most intense dust exposure of any lunar activity ever attempted. The implications for machinery lifetime are profound. On Earth, a well-maintained mining excavator might operate for 20,000 hours or more before requiring a major overhaul. The machine operates in atmosphere, with lubrication, with relatively gentle abrasive loading from rounded soil particles, with access to maintenance facilities and replacement parts. On the Moon, preliminary engineering estimates suggest that exposed mechanical systems could experience order-of-magnitude reductions in operational lifetime. A bearing designed for 10,000 hours might last 1,000. A seal designed for 5 years might fail in 5 months. A cutting edge designed for a full operational season might dull in a matter of weeks. These are not precise figures because no one has operated mining equipment on the Moon long enough to generate real wear data. They are engineering projections based on accelerated wear testing in laboratories using lunar simulant materials adjusted for the vacuum, thermal, and electrostatic conditions of the real environment. The projections could be pessimistic, but they could also be optimistic, because laboratory conditions cannot fully replicate the combined effects of vacuum, radiation, temperature cycling, electrostatic charging, and abrasive loading that machinery would experience simultaneously on the actual lunar surface. On Earth, you test for one variable at a time and hope the interactions are manageable. On the Moon, every variable attacks at once. Recent research has begun exploring mitigation strategies, and some show real promise. Electrostatic dust shields, surfaces that use oscillating electric fields to repel charged particles, have been demonstrated in laboratory settings and showed encouraging results in a NASA experiment. Specialized nanocoatings designed to reduce dust adhesion by optimizing surface polarity and conductivity are under development at institutions like the University of Central Florida. Pneumatic systems like the Planet Vac technology, tested on the Blue Ghost Mission 1 lander in March of 2025, demonstrated that compressed gas can rapidly collect surface regolith without the mechanical contact that generates the worst abrasion. These are genuine advances, and they matter. But every mitigation strategy has limits. Electrostatic shields require continuous power and only work on surfaces where the shield can be installed, not on every bearing, gear, and joint inside a complex machine. Nanocoatings wear off under abrasive loading and must be reapplied, which requires maintenance capability that does not yet exist on the Moon. Pneumatic systems avoid mechanical contact during collection but still produce dust plumes that coat surrounding equipment, and none of these technologies have been tested at the scale and duration that industrial mining would require. A technology that works for 10 minutes in a laboratory or for one sample collection on the lunar surface has not yet proven it can work for 10,000 hours of continuous excavation. The dust problem is real, it is confirmed, and it is severe. But if dust were the only obstacle, engineers might eventually design their way around it with enough clever materials, science, and robust mechanical design. The far more unsettling truth is that dust is only the first burden in a stack of compounding difficulties that make lunar mining exponentially harder than any single challenge would suggest. Every machine that survives the dust still has to survive the temperature. The lunar surface does not merely get cold at night. It plunges to temperatures where common metals become brittle, where lubricants freeze solid, where batteries lose nearly all their capacity, and where the thermal contraction of different materials at different rates can crack joints, break welds, and shatter seals that held perfectly at higher temperatures. And when the sun returns, the same surfaces that were negative 173 degrees Celsius in the dark climb to positive 120 degrees Celsius, or more, in direct sunlight. This is a swing of nearly 300 degrees experienced every 29.5 Earth days at equatorial latitudes, and experienced across distances of only meters wherever shadows fall near the poles. A machine that has been fighting dust all day must then survive this thermal assault all night, and in permanently shadowed craters, where the most valuable water ice deposits sit, the temperature never rises above negative 170 degrees. Equipment sent into those craters to mine ice must operate continuously in conditions cold enough to make standard steel crack on impact. The thermal challenge does not replace the dust challenge, it compounds it. A seal weakened by dust abrasion during excavation is more likely to fail when thermal cycling pulls it apart. A bearing already contaminated with fine abrasive particles will suffer accelerated damage when thermal expansion pushes those particles deeper into the contact surfaces. This stacking of independent problems into a single compounding burden is the central reality of lunar mining that almost no popular account conveys. Dust alone is manageable. Temperature alone is manageable. Vacuum alone is manageable. Reduced gravity alone is manageable. But dust plus temperature, plus vacuum, plus reduced gravity, plus no maintenance access, plus no supply chain, plus no atmosphere, plus continuous radiation exposure creates a combined environment where every weakness in every component is exploited simultaneously. The failure modes do not line up single file and wait their turn. They attack together, and each one amplifies the others. What this means for the machines, the power systems, and the entire infrastructure chain that lunar mining would require is the subject of what comes next. And it is where the true scale of the problem finally becomes clear. Imagine a factory on Earth where the building has no walls, no roof, and no heating system. Every 14 days the sun disappears and does not return for another 14 days. During those 2 weeks of darkness, the temperature inside the factory drops to negative 173 degrees Celsius. Metal tools left on the workbench become so cold that touching them with a bare hand would cause instant frostbite and tissue death. Lubricants in every machine freeze into brittle solids. Batteries drain to nearly zero capacity. Rubber seals harden into rigid rings that crack at the slightest flex. Every weld, every joint, every bond between dissimilar materials contracts at a different rate, generating internal stresses that accumulate with each cycle. Then the sun returns. Within hours, surfaces exposed to direct sunlight climb past 100 degrees Celsius. Those same seals that were rigid and cracked in the cold are now softening and expanding. Those same metal joints that contracted in darkness are now swelling outward. The stress is reverse. The cracks that opened in the cold are forced closed, trapping dust particles inside them, and new cracks form where thermal expansion exceeds material tolerance. This is not a thought experiment. This is the thermal environment of the lunar surface at mid-latitudes, and it repeats every 29.5 Earth days for eternity. The moon has no atmosphere. This single fact creates thermal conditions that are profoundly alien to every industrial process humans have ever designed. On Earth, air acts as a thermal buffer. It absorbs heat from hot surfaces and carries it away through convection. It insulates cold surfaces by reducing radiative heat loss. It moderates temperature swings between day and night from hundreds of degrees to mere tens. The atmosphere is so fundamental to thermal management on Earth that engineers rarely think about it. Every car engine, every power plant, every factory machine, every data center in the world depends on air to move waste heat away from critical components. Remove that air, and every thermal management strategy in terrestrial engineering ceases to function. On the moon, there is no convection. Heat cannot be transferred through a medium that does not exist. The only mechanisms available for shedding waste heat are conduction, passing heat through direct physical contact into another solid, and radiation, emitting infrared energy into space. Conduction works but is limited by the thermal properties of the regolith, which is an excellent insulator. The same powdery, vacuum-filled soil that covers the surface has extremely low thermal conductivity. Below the top few centimeters, regolith temperature barely changes regardless of whether the surface above is baking in sunlight or freezing in shadow. This means you cannot dump waste heat into the ground the way you might on Earth. The ground will not carry it away fast enough. Radiation works, but it requires large surface areas and careful design. Every piece of equipment on the lunar surface that generates heat, which is every piece of equipment that consumes power, must radiate that heat into space through dedicated radiator panels. These panels must face away from the sun and away from the hot lunar surface to maximize their effectiveness. They must maintain specific optical coatings that determine how efficiently they emit infrared radiation. And as we saw earlier, those coatings are among the first surfaces to be degraded by lunar dust. A radiator panel, coated in a thin layer of electrostatically adhered dust, begins losing its thermal performance immediately. The dust changes the surface's emissivity, its ability to shed heat as infrared radiation, and simultaneously changes its absorptivity, its tendency to absorb solar energy. The net effect is that dust-coated radiators run hotter than clean ones, reducing their cooling capacity at exactly the moment when the equipment they serve needs it most. This creates another compounding loop. Mining operations generate dust. Dust coats radiators. Coated radiators cannot shed heat efficiently. Equipment runs hotter. Hotter equipment degrades faster. Degraded equipment requires more maintenance. Maintenance requires shutting down mining. And every hour of downtime is an hour when no resources are being extracted. But every system still requires power to survive. But the damage from thermal extremes goes deeper than overheating during the day and freezing at night. The real destroyer is the cycle itself. Every material has a property called the coefficient of thermal expansion, which measures how much it grows when heated and shrinks when cooled. Different materials expand and contract at different rates. Steel expands at a different rate than aluminum. Aluminum expands at a different rate than ceramic. Ceramic expands at a different rate than the polymer used to seal the joint between them. On Earth, these differences are moderated by the narrow temperature range that most equipment experiences. A machine in a factory might see variations of 30 or 40 degrees Celsius across an entire year. The differential expansion between its materials over that range is small, easily absorbed by the elasticity of the components and the tolerances built into the design. On the Moon, the temperature range is not 30 degrees, it is 300 degrees, and it is not spread across a year. It is concentrated into a single 29-day cycle. Every bolt holding an aluminum bracket to a steel frame is being pulled and pushed by expansion forces that are an order of magnitude larger than what terrestrial engineers design for. Every adhesive bond between a thermal coating and a metal substrate is being sheared by dimensional changes that accumulate with every cycle. The first cycle might be fine, the fifth might produce a hairline crack too small to detect, the 10th widens the crack, the 20th allows dust to infiltrate through the crack into an internal volume that was supposed to be sealed. By the 50th cycle, the seal has failed, dust has reached a bearing or a circuit board, and a critical subsystem goes offline. This is thermal fatigue, and it is one of the most insidious failure modes in engineering because it produces no dramatic event. The damage is incremental, invisible, cumulative, and on the Moon, relentless. Near the poles, where lunar mining operations would most likely focus because of the water ice deposits, the thermal challenge takes on an additional dimension that has no terrestrial equivalent. At equatorial latitudes, the thermal cycle is at least predictable: 14 days of heat, 14 days of cold, a relatively uniform pattern. At the poles, the geometry of the terrain creates thermal environments that change across distances of meters rather than across timescales of weeks. A boulder casting a shadow on a flat surface creates a zone where the temperature can drop by more than 200 degrees Celsius within a few steps. A rover driving from sunlight into shadow crosses a thermal cliff. Its sunward side remains baking hot, while its shadowed side begins plunging toward cryogenic temperatures. The machine is being heated and frozen simultaneously on opposite faces. The thermal stresses this generates are not the uniform expansion and contraction of a day-night cycle. They are differential stresses, warping and twisting the structure as one side expands while the other contracts. A structural beam heated on one face and frozen on the other bows like a bimetallic strip. Connections between components on opposite sides of the thermal gradient are pulled apart. Wiring harnesses that cross the boundary between hot and cold zones experience flexing loads they were never designed to endure. Any mining vehicle operating near the poles must cross these thermal boundaries repeatedly as it moves between illuminated processing sites and shadowed mining targets. Every crossing inflicts a fresh set of stresses on a structure already weakened by dust abrasion and prior thermal cycling. The machine does not get a clean start each time. Damage accumulates, microcracks propagate, fasteners loosen imperceptibly, and at some point, a component that has survived 100 crossings fails on the 101st, not because that crossing was different, but because the cumulative damage from all 100 previous crossings finally exceeded the material's tolerance. The temperature extremes are bad enough at equatorial and mid-latitude sites, but the locations where the most valuable lunar resource sits are thermally worse in ways that are difficult to overstate. Water ice on the Moon has been confirmed in permanently shadowed regions near the South Pole. These are craters and depressions where the geometry of the terrain and the small axial tilt of the Moon, only about 1.5 degrees, combine to ensure that the crater floors never receive direct sunlight. They have not been illuminated for billions of years. Without any solar input and without any atmosphere to redistribute heat, these permanently shadowed regions have reached thermal equilibrium with deep space. Temperatures in the coldest permanently shadowed craters have been measured by the Lunar Reconnaissance Orbiter at approximately 50 Kelvin, which is negative 223 degrees Celsius. That is colder than the surface of Pluto, colder than anywhere on Mars. Among the coldest stable temperatures measured anywhere in the solar system outside of deep space itself, at negative 223 degrees Celsius, the engineering challenges are not just amplified versions of the problems at warmer sites. They are qualitatively different. Common structural steels undergo a transition from ductile to brittle behavior at temperatures well above this range. A steel component that would bend gracefully under stress at room temperature can shatter like glass at cryogenic temperatures. Aluminum alloys retain ductility better at extreme cold, which is why they are preferred for cryogenic applications, but they still lose toughness and fatigue life. Polymers and elastomers used in seals, gaskets, and cable insulation become rigid and fragile. Standard electronics fail outright because semiconductor behavior changes at cryogenic temperatures, and batteries based on lithium-ion chemistry lose virtually all their capacity below -40°C, let alone -200. Any machine sent into a permanently shadowed crater to mine water ice must either be built entirely from materials that function at cryogenic temperatures, which is possible but enormously constrains design choices and increases cost, or it must carry its own internal heat source, powerful enough to keep critical components warm against the relentless radiative heat loss into a surrounding environment that is barely above absolute zero. Keeping electronics at a survivable operating temperature of, say, -20°C, when the external environment sits at -220, requires a continuous heat input that must be sustained for the entire duration of operations. There is no break. There is no warming period. The cold is permanent. This is where the power problem converges with the thermal problem and creates a burden far greater than either one alone. Solar power is the most straightforward energy source for the lunar surface. The sun delivers approximately 1,367 watts per square meter to the moon, unfiltered by atmosphere, which is actually more consistent than solar energy on Earth. During the lunar day at equatorial latitudes, solar panels can generate substantial power, but the lunar day at equatorial sites lasts roughly 14 Earth days, followed by 14 Earth days of total darkness. During that darkness, solar panels produce nothing. Any system that depends on solar power must either shut down for 2 weeks out of every 4, which is incompatible with continuous mining operations, or it must store enough energy during the day to last through the night, which requires battery banks of extraordinary size and mass. The numbers are punishing, and they deserve to be walked through in detail because they reveal just how quickly the mass penalties spiral beyond anything a reasonable mission can deliver. 1 watt of continuous heater power sustained through a 14-day lunar night requires roughly 5 kilograms of battery mass, using current lithium-ion technology. That is 5 kilograms just to keep 1 watt flowing for 336 hours of darkness. Now consider what even a modest lunar mining demonstration would need. A small regolith processing experiment, something capable of extracting perhaps a few kilograms of oxygen over a lunar day, might require 5 kilowatts of electrical power during active operations, and at least 500 watts of continuous survival heating to keep its electronics and mechanisms alive through the night. 500 watts times 5 kilograms per watt equals 2,500 kilograms of batteries dedicated solely to overnight thermal survival. 2.5 metric tons, just to keep the lights on and the heaters running during 2 weeks of darkness. Not to do any mining, not to process any regolith, not to transport any material, just to survive long enough to resume work when the sun comes back, and that 2.5 tons of batteries must itself be delivered from Earth at current commercial lunar delivery costs. At roughly $1 million per kilogram for end-to-end delivery to the lunar surface using current generation landers, the overnight survival battery bank alone would cost on the order of $2.5 billion to deliver. For a demonstration experiment, the numbers are so extreme that they make the case for nuclear power almost by default, not because nuclear is easy, but because the alternative is economically absurd. The polar regions offer a partial solution. Certain elevated locations near the South Pole, the rims of craters and peaks of ridges, receive sunlight for much longer fractions of the lunar day because of their height and orientation. Some of these so-called peaks of eternal light receive illumination for 80 to 90% of the year, though true permanent sunlight has not been confirmed at any location. A solar-powered base on one of these elevated sites would have greatly reduced energy storage requirements. But there is a cruel geometric catch. The permanently shadowed craters where water ice exists are located at the bottoms of depressions directly adjacent to these illuminated peaks. The mining target sits in permanent darkness. The power source sits in near-permanent light. The two are separated by terrain that includes steep crater walls, boulder fields, and some of the most rugged topography on the lunar surface. This means you cannot simply place your solar panels next to your mining equipment. You must generate power on the crater rim and transmit it down into the crater, either through physical cables routed across difficult terrain or through beamed power systems like lasers or microwaves. Both approaches are technically feasible. Neither is simple. Physical cables must be manufactured to survive the lunar environment. They must be flexible enough to route across uneven terrain, resistant to abrasion from regolith contact, tolerant of the full thermal range from cryogenic shadow to sunlit exposure, and robust against degradation from ultraviolet radiation and charged particle bombardment. Every meter of cable is a potential failure point. A single break in a power cable running from a crater rim down a boulder-strewn slope into permanent shadow would cut power to every piece of mining equipment below. Repairing that cable requires sending a crew or robot down the same treacherous slope, locating the break, and performing a splice in vacuum, in darkness, wearing gloves designed for radiation protection rather than fine motor tasks. The cable itself becomes another piece of infrastructure that must be maintained in an environment hostile to maintenance. Beamed power eliminates the physical cable, but introduces its own complications. A laser or microwave transmitter on the crater rim must maintain precise alignment with a receiver on the crater floor. The distances involved are not enormous, perhaps a few hundred meters to a couple of kilometers, but the alignment must be sustained against thermal expansion of the mounting structures, settling of the regolith under equipment weight, and any vibration from nearby mining activity. A misaligned beam wastes power, or worse, deposits energy on unintended targets. The receiver must convert beamed energy back to electricity with reasonable efficiency while operating at cryogenic temperatures, and its receiving surface must remain clean enough to function, which in the dusty environment near active mining operations is a continuous challenge. Every solution to the power distance problem introduces new subsystems that themselves require power, maintenance, and protection from the lunar environment. The web tightens. Nuclear power offers an alternative that eliminates the day-night cycle problem entirely. Radioisotope thermoelectric generators, or RTGs, convert the decay heat of radioactive isotopes, typically plutonium-238, into electricity. They work continuously regardless of sunlight and have powered deep space missions for decades. NASA's Curiosity and Perseverance rovers on Mars each carry an MMRTG that produces roughly 110 watts of electrical power. This is enough to operate a rover, but nowhere near enough to power industrial mining and processing equipment. A regolith processing reactor capable of extracting oxygen at meaningful rates would need tens of kilowatts at minimum. You would need hundreds of RTGs to reach those power levels, and the global supply of plutonium-238 is extremely limited. The United States restarted production in 2015 after years without domestic supply, but output remains small, measured in kilograms per year, rather than the tons that industrial lunar power would demand. Fission reactors represent the most promising nuclear option for large-scale lunar power. NASA's KiloPower project, which demonstrated a small fission reactor prototype called Krusty in 2018, showed that a reactor producing 1 to 10 kilowatts of electrical power could be built at a mass of roughly 1,500 kilograms. Multiple units could be deployed to provide tens of kilowatts. This is a genuine path toward the power levels that industrial operations would require. But fission reactors on the Moon face their own challenges. They produce waste heat that must be radiated away, requiring the same radiator systems vulnerable to dust degradation. They require shielding to protect nearby equipment and any human operators from radiation. And they represent a technology that has never been operated on any planetary surface. The gap between a ground test and sustained lunar operation is the same gap that confronts every other lunar technology. Plausible in principle, unproven in practice, and subject to the same compounding environmental stresses that degrade everything else. China's Chang'e 3 lander and its U-2 rover, which reached the Moon in 2013, survived multiple lunar nights using radioisotope heater units, combined with thermal insulation. U-2, delivered by Chang'e 4 to the far side of the Moon in 2019, has been operating for years, surviving dozens of lunar night cycles, These are genuine achievements in thermal survivability, but they were achieved with a rover weighing approximately 140 kilograms, performing light scientific tasks, spending each lunar night in a hibernation mode where it does no useful work. Scaling from a hibernating micro-rover to an industrial mining system operating continuously through lunar night is not a linear problem. It is an exponential one, where every increase in capability demands disproportionate increases in power, thermal management, and structural robustness. And all of this leads into the problem that ties every other problem together and makes the entire chain feel almost impossible: maintenance. On Earth, maintenance is the invisible backbone of every industrial operation. Machines break, components wear out, seals fail, software glitches, calibration drifts, filters clog, belts snap, bearings seize. This is not failure, this is normal operation. Every machine ever built requires periodic maintenance to continue functioning, and the more aggressively a machine is used and the harsher its operating environment, the more frequently maintenance is required. Terrestrial mining operations dedicate enormous resources to maintenance. Major mining companies employ full-time maintenance crews, numbering in the hundreds per site. Spare parts, warehouses, stock thousands of components. Specialized repair equipment, cranes, welding rigs, diagnostic tools is available on site. When a haul truck breaks down in an open-pit mine on Earth, a mechanic drives over in a service vehicle carrying the replacement part, performs the repair in hours, and the truck is back in operation by the next shift. On the Moon, none of this exists. There are no mechanics, there are no service vehicles, there are no spare parts warehouses. The nearest replacement component is on Earth, 380,000 kilometers away, and getting it to the lunar surface requires a rocket launch, a transit of several days, a precision landing, and an unpacking and installation process that must be performed either by an astronaut in a spacesuit with limited dexterity and visibility, or by a robot that itself requires maintenance. The cost of delivering 1 kilogram of payload to the lunar surface is currently measured in tens of thousands of dollars using commercial lunar lander services. A single replacement bearing that weighs half a kilogram and costs $50 on Earth becomes a $50,000 component on the Moon. And that is only the launch cost, not the engineering cost of designing the replacement for lunar conditions or the operational cost of installing it. This economic reality transforms the maintenance problem from an inconvenience into a potential mission killer. Every component of a lunar mining system must either be designed to last the entire operational lifetime without maintenance, which is nearly impossible in the abrasive, thermally cycling, vacuum environment of the Moon, or the system must include the capability to perform its own maintenance autonomously. Self-maintaining machinery is an active area of robotics research, but the current state of the art is far from what lunar mining would require. Autonomous robots can perform simple, repetitive tasks in controlled environments. They cannot yet diagnose unexpected failure modes, improvise repairs with available materials, or adapt to damage patterns that were not anticipated by their designers. To understand how devastating the maintenance gap really is, walk through what happens when a single component fails in a lunar mining system. Suppose a regolith excavator has been operating for 3 months at the edge of a permanently shadowed crater. Dust has been infiltrating its drive motor bearings since the first day of operations despite hardened seals. Thermal cycling across the shadow boundary has been fatiguing the bearing housing at every shift change. On day 91, the left drive motor bearing seizes. The excavator stops. It cannot move to the processing site. It cannot move out of the path of other equipment. It sits in place, still consuming survival heater power, contributing nothing. The processing plant downstream, which depends on a steady supply of excavated regolith, now has no feedstock. It has 2 choices. It can shut down and enter survival mode, consuming power to keep warm but producing nothing, which wastes the energy invested in heating and preparing the reactor. Or it can continue operating on whatever regolith stockpile exists at the processing site, which will be exhausted quickly, because in an environment where transport is this expensive, large buffer stockpiles are a luxury that mass budgets rarely allow. Meanwhile, the transport vehicle that carries regolith from excavator to processor has nothing to carry. It too sits idle, consuming survival power, accumulating dust, thermally cycling, degrading. Every machine in the chain is losing operational lifetime while the chain is broken. And the bearing that caused the failure cannot be replaced. There is no spare on the Moon. A replacement must be launched from Earth. Assuming one is available and a launch window exists, the fastest possible delivery is several days of transit plus landing, site delivery, and installation. Realistically, the delay could be weeks or months. During that entire time, the full mining system is offline, while every component in it continues to be attacked by the environment. Now multiply this scenario by every bearing, every seal, every gear, every valve, every electrical connection, every sensor, every actuator in every machine in the system. Each one is a potential single point of failure, capable of cascading through the entire chain. On Earth, redundancy and rapid maintenance absorb these failures routinely. On the Moon, each failure is a crisis that can only be answered by waiting for Earth or by having pre-positioned spares that are themselves degrading in storage. The alternative is to design modular systems where entire subsystems can be swapped out rather than repaired in place. A rover with a worn-out drill assembly could dock with a maintenance station, eject the old assembly, and receive a new one. This approach reduces the complexity of on-site repairs but shifts the burden to logistics. Every replaceable module must be pre-positioned on the lunar surface, which means it must be launched from Earth, landed, stored, and protected from the same environment that destroys operating equipment. Storing spare modules on the lunar surface for months or years while waiting to be needed exposes them to dust accumulation, thermal cycling, and radiation damage before they are ever used. The spare part begins degrading from the moment it arrives. Crude maintenance offers more flexibility, but at staggering cost. Keeping astronauts on the lunar surface requires life support, habitat infrastructure, food, water, radiation protection, medical capability, and regular resupply, all of which consume resources and mission capacity that compete directly with mining operations. The Artemis program is targeting its first crewed lunar landing, with Artemis 4 in 2028, with the ambition of yearly landings thereafter. But these early missions will be brief surface stays, focused on exploration, not industrial maintenance. The infrastructure needed to support a permanent maintenance crew on the Moon is itself a major engineering challenge that depends on the very in-situ resource utilization capabilities that maintenance is supposed to enable. This circularity is the defining characteristic of the lunar mining problem, and it is what makes the challenge fundamentally different from any industrial problem humanity has solved on Earth. On Earth, you build infrastructure using existing infrastructure. Roads are built by trucks that drive on older roads. Factories are constructed by cranes powered by existing power plants. Supply chains feed on supply chains. The entire industrial ecosystem rests on a foundation of pre-existing capability that accumulated over centuries. On the Moon, there is no foundation. Every capability must be created from scratch, in an environment that punishes the creation process. Building a processing plant requires construction equipment. The construction equipment requires power. The power system requires installation. The installation requires transport. The transport requires fuel. Producing fuel requires a processing plant. At every step, the dependency loops back on itself, and at every step, the lunar environment is degrading every component involved. The honest term for this situation is a bootstrapping problem. You need industrial capability to build industrial capability, but you have no industrial capability to start with. The only way to break into the loop is to bring the initial capability from Earth at enormous cost per kilogram and hope that it survives long enough on the lunar surface to begin producing something useful before the environment destroys it. This is why every credible lunar ISRU roadmap begins with very small demonstration missions and scales up incrementally over decades, rather than attempting industrial operations immediately. The Blue Ghost mission's PlanetVac test in 2025 collected a few scoops of regolith in a few seconds. The next step might be a small processing experiment that extracts a few grams of oxygen from a few kilograms of soil, then perhaps a larger experiment over a full lunar day, then an attempt to survive a lunar night, then a longer duration test, spanning multiple thermal. Each step tests whether equipment can survive the environment long enough to be useful, and each step reveals new failure modes that must be solved before the next step can proceed. This is not pessimism. It is engineering reality. Humans went from the first powered flight to landing on the moon in 66 years. The ingenuity is not in question. What is in question is the timeline and the cost, because the lunar environment imposes penalties at every stage that have no terrestrial equivalent. A machine that works perfectly in a laboratory on Earth may fail within weeks on the lunar surface. A processing concept that is thermodynamically efficient on paper may be practically impossible when your containment vessel is being abraded from the outside, thermally cycled to destruction, and starved of the power needed to maintain operating temperature. The stack of challenges, dust-destroying equipment, thermal extremes fatiguing every material, vacuum eliminating conventional cooling and lubrication, power limitations constraining every operation, and maintenance impossibility closing every escape route, does not present a single wall to be scaled. It presents a tightening web where solving one problem shifts the burden to another without reducing the total difficulty. Making equipment dust-resistant often means making it heavier, which increases the cost to deliver it from Earth. Adding thermal protection increases mass and power consumption. Increasing power capacity requires larger solar arrays or nuclear systems, which require more structure, more radiators, more maintenance. Every solution feeds back into the problem it was meant to solve. The machines we send to the moon to begin mining will not just be digging for resources. They will be fighting the moon itself, an environment that corrodes, abrades, freezes, bakes, and starves every system we know how to build. Understanding why anyone would still attempt this, and what the real economics and engineering of lunar resource utilization actually look like when stripped of optimism, requires confronting the full picture of what it takes to turn raw regolith into something humanity can actually use. That confrontation comes next. Strip away the concept art. Forget the animated videos of gleaming rovers trundling across a pristine grey plain, dumping loads of regolith into a sleek processing hopper, while astronauts monitor progress from a nearby habitat dome. Forget the revenue projections. Forget the pitch decks with hockey stick growth curves and trillion-dollar addressable markets. Ask instead the most basic question that any mining engineer on Earth would ask before breaking ground on a new operation. What exactly are you planning to do with the rock once you dig it up? On Earth, this question has answers backed by centuries of operational experience. You crush ore to a target particle size. You separate valuable minerals from waste using gravity, flotation, magnetic fields, or chemical leaching. You smelt or refine the concentrate in furnaces or reactors that operate at precisely controlled temperatures and pressures. You transport the product to market using trucks, trains, ships, or pipelines. Every step uses water, air, gravity, and cheap energy in quantities so vast that most people never think about them. A single iron ore operation might burn through 50,000 litres of diesel fuel per day just to keep its haul trucks running. A single aluminum smelter draws electrical power equivalent to a small city. The infrastructure is enormous, but it is supported by an economy where roads, power grids, labour, and replacement parts are abundant and relatively inexpensive. On the moon, the question of what you do with the rock leads into a chain of processes that have been proposed, modelled, and in some cases tested in laboratories on Earth, but never demonstrated at any scale on the actual lunar surface. The leading candidates for extracting useful products from lunar regolith each carry their own distinct engineering burdens, and understanding them reveals why the gap between concept and reality remains so wide. Molten regolith electrolysis is perhaps the most conceptually straightforward approach. You heat raw regolith to approximately 1,600 degrees Celsius until it melts into a liquid, then pass an electric current through the molten material. The oxygen ions in the melt migrate to the anode, where they are released as oxygen gas. The metals, primarily iron, silicon, aluminum, and titanium, collect at the cathode. In principle, this process converts the most abundant component of lunar soil directly into two useful products: breathable oxygen and structural metals. No chemical reagents need to be imported from Earth. The feedstock is literally the ground beneath your feet. In practice, the difficulties are severe. 1,600 degrees Celsius exceeds the melting point of most common container materials. The crucible that holds the molten regolith must be made from something that can withstand sustained contact with a corrosive silicate melt at temperatures that would destroy steel, aluminum, and most ceramics used in terrestrial industry. Candidate materials include certain refractory metals like iridium or platinum, or specialized oxide ceramics, all of which are expensive, difficult to fabricate, and themselves subject to slow degradation from the aggressive melt chemistry. The electrodes must survive immersion in the same liquid and carry high current densities without corroding. Anode materials in particular face intense chemical attack from the nascent oxygen being liberated at their surfaces. In a terrestrial laboratory, these problems are real but manageable. Crucibles crack after a few runs, and a technician replaces them from a storage shelf. Electrodes corrode, and a researcher installs a fresh set between experiments. The ambient temperature of the laboratory is 20 degrees Celsius, meaning the energy cost of reaching 1600 degrees starts from a comfortable baseline, and the room's air conditioning prevents the exterior of the crucible housing from overheating. On the Moon, every one of these background conditions vanishes. The starting temperature of the feedstock could be negative 170 degrees in a normal location, or negative 220 in a permanently shadowed zone, which means the energy required to reach operating temperature is vastly greater than on Earth. The crucible housing cannot shed heat by convection, so external surfaces radiate intensely, while internal surfaces must contain a molten pool, creating thermal gradients across the vessel wall that accelerate fatigue cracking. And when the crucible does crack, as it inevitably will, there is no shelf of replacements. There is a 3-day minimum delivery window from Earth, and the cracked vessel may have already leaked molten silicate onto other equipment, causing secondary damage that itself requires repair. The power demand is enormous. Heating regolith from ambient lunar temperature to 1600 degrees positive requires a staggering energy input per kilogram of feedstock. Maintaining the melt at operating temperature against radiative heat losses in vacuum demands continuous power that dwarfs the output of any solar panel array or radioisotope generator currently designed for lunar use. Realistic estimates suggest that a processing plant capable of producing even 1 metric ton of oxygen per year would require tens of kilowatts of continuous electrical power dedicated solely to the electrolysis process, not counting the power needed for excavation, transport, thermal management, dust mitigation, communication, and equipment survival. Scaling to industrially meaningful output rates would push power requirements into the hundreds of kilowatts or beyond. Hydrogen reduction offers a lower temperature alternative. In this process, hydrogen gas is passed over heated regolith at temperatures around 900 to 1100 degrees Celsius. The hydrogen reacts with iron oxide in the regolith, stripping oxygen atoms from the iron and combining with them to form water vapor. The water is then collected and electrolyzed into hydrogen, which is recycled back into the process, and oxygen, which is the desired product. This approach works best with ilmenite-rich regolith, a titanium iron oxide mineral that is relatively common in the dark volcanic plains called Maria. The advantage is lower operating temperature than molten regolith electrolysis. The disadvantage is that you need a supply of hydrogen to start the cycle, and hydrogen is one of the most difficult gases to contain, because its tiny molecular size allows it to diffuse through materials that would hold larger gas molecules. In vacuum, any hydrogen that escapes a reactor vessel is lost to space permanently. The system must achieve extremely high recovery rates to remain viable, because importing replacement hydrogen from Earth defeats the purpose of using local resources. On Earth, hydrogen leaks from industrial systems are routine and manageable. You detect the leak, patch the fitting, vent the room, and resume operations. The hydrogen that escaped disperses into the atmosphere and is eventually replaced from industrial gas suppliers at modest cost. On the Moon, every molecule of hydrogen that leaks through a seal weakened by thermal cycling or dust abrasion is a molecule that has been permanently subtracted from the process inventory. There is no atmosphere to catch it. There is no supplier to replace it. The loss is irreversible. Over weeks or months of continuous operation, even small leak rates compound into significant inventory depletion, and the entire closed-loop process begins losing efficiency. Eventually, if losses are not controlled, the system can no longer function without resupply from Earth, which converts what was supposed to be a locally sourced operation back into an Earth-dependent one. Carbothermal reduction uses carbon, typically in the form of methane, as the reducing agent instead of hydrogen. Methane reacts with metal oxides in heated regolith to produce carbon monoxide and free metals, and the carbon monoxide can itself be processed to recover the carbon for recycling. This method can access a wider range of oxide minerals than hydrogen reduction, making it applicable to more types of lunar soil. But it requires an initial supply of carbon, which is extremely scarce on the Moon, and it generates intermediate compounds that must be carefully managed in a closed-loop system where any loss of carbon to space is essentially permanent. Each of these processes has been demonstrated at laboratory scale on Earth, using lunar simulant materials in conditions that approximate some aspects of the lunar environment. None has been tested in actual vacuum, at actual lunar temperatures, with actual lunar regolith, under actual thermal cycling and dust conditions, for durations longer than a few hours. The difference between a laboratory demonstration and sustained industrial operation is not a matter of scaling up. It is a matter of surviving. A laboratory reactor operates in a controlled room with stable temperature, atmospheric pressure, available utilities, and technicians who can intervene when something goes wrong. A lunar reactor operates in vacuum, in temperature extremes, bombarded by radiation, coated in abrasive dust, with no technician within 3 days travel time. Every material choice that works adequately in a laboratory may fail under the compounded stresses of the real environment. Water ice extraction presents a different set of challenges, but the cumulative burden is no lighter. The leading approach is thermal mining. You identify a deposit of ice-bearing regolith in a permanently shadowed crater, enclose a volume of the surface under a sealed tent or dome, and apply heat to raise the temperature above the point where water ice sublimates directly from solid to vapor in vacuum. The vapor is captured, channeled to a cold surface, and condensed back into ice or liquid water for storage. The concept is simple. The execution is ferocious. First, you must operate in permanent darkness at temperatures around -220 degrees Celsius. Every piece of equipment must be actively heated just to function, consuming power that must be generated elsewhere and transmitted into the crater. Second, the regolith you are heating is the same abrasive, electrostatically charged material that destroys equipment everywhere else on the Moon, and the thermal cycling between the heaters and the ambient cryogenic environment adds fatigue stresses to every enclosure and seal. Third, the concentration of water ice in the regolith is not high. Orbital estimates suggest 2 to 10% by weight in the richest deposits. This means that for every kilogram of water you extract, you must heat and process somewhere between 10 and 50 kilograms of regolith. At cryogenic starting temperatures, the energy cost per kilogram of water recovered is substantial. Fourth, the water vapor produced must be captured with very high efficiency, because in vacuum, any molecule that escapes the collection system disperses ballistically across the surrounding terrain and is irretrievable by the operation that produced it. The enclosure must maintain a seal against a surface made of jagged, irregular particles that resist forming airtight contacts. A seal that leaks even slightly represents a continuous loss of the product you are trying to collect. Fifth, and perhaps most importantly, no one has confirmed the physical state and distribution of water ice in these deposits with ground truth measurements. Orbital data tells us that hydrogen-bearing compounds are present. Impact experiments confirmed water in ejected debris, but we have not drilled into a permanently shadowed crater, pulled up a core sample, and measured the ice content directly. We do not know what the ice actually looks like at the grain level, and this uncertainty is not a minor detail. It is the single most consequential unknown in all of lunar resource planning, because the physical form of the ice determines everything about how you would design a system to extract it. Consider the possibilities. If the ice exists as discrete centimeter-scale chunks or pebbles mixed into otherwise dry regolith, you might be able to separate it mechanically, screening or sieving the material to concentrate ice-rich fragments before applying heat. This would drastically reduce the energy cost per kilogram of water recovered, because you would only need to heat a small fraction of the excavated mass. The processing plant could be simpler, lighter, and less power-hungry. But if the ice exists as a molecular-thin frost-coating individual regolith grains, mechanical separation becomes useless. Every grain carries a tiny amount of water on its surface, and liberating that water requires heating every grain to sublimation temperature. The energy cost per kilogram of water recovered climbs enormously because you are heating tens of kilograms of rock to extract grams of ice. The processing plant must be larger, more power-intensive, and capable of handling far greater throughput to produce the same yield. A third possibility is that the ice exists as interstitial cement-binding regolith grains together into a weakly consolidated aggregate. In this case, the regolith in ice-rich zones would not behave like loose powder at all. It would resist excavation like a soft rock, requiring cutting or percussive force rather than simple scooping. Every assumption about excavation equipment, bucket design, energy consumption per scoop, and wear rates on cutting edges changes if the target material is cemented aggregate rather than loose soil. And a fourth possibility, which many researchers consider the most likely, is that the ice exists in some combination of all these forms, varying unpredictably with depth, lateral position, and the geological history of each individual crater. A mining system designed for one form of ice might encounter another form meters away and find itself unable to process the material efficiently. Each physical form implies a different excavation method, a different energy budget, a different processing architecture, and a different throughput rate. An ice extraction system optimized for frost-coated grains would be wastefully oversized for chunk ice. A system designed for loose regolith would fail on cemented aggregate. Without knowing which form dominates, or whether any single form dominates at all, engineers cannot optimize their designs. They must either build systems flexible enough to handle every possibility, which adds mass, complexity, and cost, or they must guess and accept the risk that the guess is wrong. The Viper rover was specifically designed to answer these questions. Its drill would have penetrated to 1 meter depth in permanently shadowed regolith, and its instruments would have measured not just whether water was present, but in what physical state, at what concentration, and how those properties changed with depth. Its cancellation means those answers remain unknown. Without ground truth, every engineering design for ice extraction is based on assumptions about a resource whose physical character has never been directly observed. The entire multi-billion-dollar vision of lunar water mining rests on a foundation that no one has tested with a single drill hole. Interloon, a Seattle-based company, has been developing an electric excavator prototype in partnership with Vermeer, a well-known earth-moving equipment manufacturer. The prototype is designed to process 100 metric tons of lunar regolith per hour to extract helium-3, with a target of deploying a pilot harvesting plant on the Moon by 2029, preceded by a validation mission in 2027. This is an ambitious timeline by any standard, and it illustrates the scale of processing that would be needed for even a modestly valuable product. Helium-3 concentrations in lunar soil are measured in parts per billion. Extracting meaningful quantities requires moving and heating enormous volumes of regolith, essentially strip mining the surface and processing the soil through thermal separation systems designed to liberate tiny quantities of gas from each batch. The excavation rates, power demands, and equipment wear associated with this volume of material handling are staggering, and no comparable operation has ever been attempted outside of Earth's atmosphere. Transport adds another stratum of difficulty that is easy to overlook but may ultimately prove as punishing as any processing challenge. On Earth, transport is so routine that it barely registers as a cost factor for most mining operations. Trucks drive on roads. Trains run on rails. Conveyors carry material uphill and downhill on continuous belts. All of these systems depend on gravity for traction, on atmosphere for cooling, and on maintenance infrastructure for sustained operation. On the Moon, there are no roads. Building roads from sintered regolith has been proposed, but sintering regolith requires energy and equipment that itself must be transported to the site. Without roads, wheeled or tracked vehicles must traverse raw regolith, dealing with reduced traction from low gravity, dust infiltration of drive systems, and terrain that includes boulders, slopes, and crater rims with no grading or preparation. Moving material from a mining site in a permanently shadowed crater to a processing facility on an illuminated crater rim means traversing some of the most rugged terrain on the Moon. The elevation difference between a crater floor and its rim can be hundreds of meters, at slopes exceeding 15 to 20 degrees in many candidate sites near the South Pole. Consider what it takes to drive a loaded transport vehicle up that slope. On Earth, a haul truck carrying 40 tons of ore up a 10-degree ramp relies on friction between rubber tires and compacted gravel, in a gravitational field of 9.8 meters per second squared, with an engine cooled by airflow across a radiator. On the Moon, you have 1/6 the gravitational force pressing your wheels into the surface, which means 1/6 the traction available to push the vehicle forward. You have no rubber tires because rubber becomes brittle at cryogenic temperatures, so you are using metal wheels or tracks that grip poorly on loose, powdery regolith. You have no air cooling for your drive motor, so waste heat must be radiated away through surfaces that are accumulating dust. And you are climbing a slope covered in regolith that has never been compacted by rain, traffic, or any natural process, a surface so loose that wheels can sink and spin without gaining purchase. Every trip up that slope grinds abrasive regolith into the vehicle's wheels, bearings, and drivetrain. Every trip exposes the vehicle to thermal gradients as it moves from cryogenic shadow into sunlight. Every trip consumes power that must come from finite onboard reserves or be beamed from a remote source, and every kilowatt-hour spent on transport is a kilowatt-hour not available for processing or survival heating. And every trip must be followed by a return trip, back down into the crater, empty, to collect another load. The energy cost of transporting regolith even modest distances on the lunar surface is dramatically higher per ton-kilometre than any terrestrial mining operation, because every supporting system that makes Earth transport efficient is absent. The logistics compound further when you consider throughput. If a processing plant needs 10 tons of regolith per day to produce a useful quantity of oxygen, and a transport vehicle can carry 500 kilograms per trip, you need 20 trips per day. 20 ascents up a crater wall, 20 descents back down, each one wearing the vehicle, each one consuming power, each one exposing the machine to the full stack of environmental stresses. The transport vehicle may need maintenance more frequently than any other machine in the system, precisely because it experiences the most varied and extreme conditions, the most terrain contact, and the most thermal boundary crossings. Now step back and look at the full chain. You must survey a site to confirm resource concentration. You must deliver excavation equipment from Earth at tens of thousands of dollars per kilogram. You must power that equipment continuously through extremes of temperature and darkness. You must dig abrasive regolith that destroys your equipment progressively with every scoop. You must transport the excavated material across unimproved terrain to a processing facility. You must heat the material to extreme temperatures or pass reactive gases through it in sealed vessels that degrade under thermal cycling and abrasion. You must capture and store the products, whether oxygen, water, or metals, in containers that maintain integrity in vacuum. You must maintain every machine in this chain against wear rates that far exceed terrestrial norms, using spare parts that must either be launched from Earth or manufactured on site with equipment that itself requires maintenance. You must power the entire operation, the mining, the processing, the transport, the maintenance, and the survival heating through lunar night, from an energy source that must be delivered, installed, and protected from the same environment destroying everything else. Failure at any single point in this chain does not merely reduce output. It cascades. A transport vehicle breakdown strands excavated material at the dig site. A processing reactor failure wastes the energy already spent on excavation and transport. A power system degradation forces everything to operate at reduced capacity, extending the time each piece of equipment spends exposed to the environment, accelerating wear, increasing the probability of the next failure. The chain does not just add difficulties together, it multiplies them. This is what it means to say that mining the moon is an infrastructure problem as much as a resource problem. The resources exist. The physics of extraction is understood. The chemistry works in laboratories. But the infrastructure required to execute these processes on the lunar surface, to sustain them, to repair them, to power them, to protect them from an environment that degrades every component simultaneously, constitutes a challenge that dwarfs the simple act of finding something valuable in the ground. On Earth, infrastructure is the invisible foundation that makes every industrial operation possible. On the moon, infrastructure does not exist. It must be built from scratch, in a hostile environment, using tools that the environment is destroying while you use them. Compare this to any mine on Earth. Even the most remote terrestrial mining operation in the Australian outback, in the Canadian Arctic, in the Atacama Desert, operates within an atmosphere that provides cooling, within a gravitational field that provides traction, with access to water for processing, with a supply chain reachable by truck or aircraft within hours, with maintenance crews on call, with replacement parts in warehouses, with power grids or diesel generators backed by readily available fuel. Remove every one of those advantages. Replace them with vacuum, abrasive dust, cryogenic temperatures, 2-week darkness, 3-day resupply latency, and an environment where nothing heals, nothing settles, and nothing wears smooth. What remains is not mining as we understand it. It is industrial survival. Some of the commercial ventures now pursuing lunar resources understand this honestly. Their roadmaps begin with extremely small demonstrations and scale up over decades. They speak of minimum viable products, of buying down risk incrementally, of proving that a single process step works on the surface before attempting the next. This is the right approach, and it mirrors how every major industrial frontier has been developed throughout history. The first oil wells were modest affairs. The first semiconductor fabrication plants were tiny. New industrial capability grows through iterative learning, and lunar industry will be no different. But the timeline implied by this iterative approach is far longer than the breathless headlines suggest. We are not 10 years away from mining the moon in any industrially meaningful sense. We are likely decades away from sustained production of even small quantities of lunar water or oxygen on the surface. The first crewed Artemis landing has not yet occurred. The first long-duration surface mission remains years beyond that. The first dedicated ISRU demonstration at meaningful scale is still in the concept phase. And every step along that path will encounter surprises, failures, and setbacks driven by an environment that punishes optimistic assumptions. None of this means that lunar mining is impossible. It means that it is harder than it sounds. Dramatically, fundamentally, stubbornly harder. The moon is not a warehouse with bad logistics. It is an environment that actively resists industrial activity. Dust grinds machinery. Vacuum eliminates lubrication and cooling. Thermal extremes fatigue every material. Power is scarce and expensive. Maintenance is nearly impossible. Transport is punishing. Processing requires enormous energy. And every one of these burdens compounds every other, creating a system-level difficulty that is vastly greater than the sum of its parts. The real shock is not that the moon has resources. Humanity has known that for decades. The real shock is what it takes to turn those resources into something usable. It requires building and maintaining an entire industrial chain, from excavation to processing to transport to storage, in a place where every link in that chain is under constant attack by the environment. Not one catastrophic obstacle, not one dramatic failure, just a relentless, grinding, compounding accumulation of wear, damage, degradation, and energy cost that makes every gram of extracted material more expensive and more difficult than the last. And that is perhaps the deepest lesson the moon has to teach us before we have even begun. We are a species accustomed to frontiers that yield. We cut forests and they became farmland. We dug mines and they produced ore. We drilled wells and they delivered oil. Every terrestrial frontier, no matter how harsh, eventually surrendered to the accumulated weight of infrastructure, labour, and iterative improvement. The Arctic was hostile, but roads and insulated buildings and diesel heaters tamed it. The deep ocean was inaccessible, but submersibles and remotely operated vehicles opened it. Every time humanity encountered a difficult environment on Earth, we built systems to neutralize the difficulty, and the environment cooperated by staying neutral in return. Rock does not fight back. Seawater does not corrode your ship faster because you started pumping oil. Arctic cold does not intensify because you built a road. The moon is different. The moon fights back. The act of mining generates dust that accelerates the destruction of mining equipment. The act of processing creates thermal gradients that fatigue the vessels doing the processing. The act of transporting material grinds the transport vehicles into the surface that is wearing them down. Every industrial activity on the moon makes the environment locally worse for industrial activity. The feedback is negative. The harder you push, the harder the moon pushes back. And unlike any terrestrial frontier, there is no moment when the environment relents. There is no taming. There is no equilibrium where human systems and lunar conditions reach a stable accommodation. The dust never rounds itself smooth. The vacuum never fills with air. The thermal cycles never moderate. The abrasion never stops. The moon does not refuse us its resources. It simply demands that we earn them in ways we have never had to earn anything before. Every ton of lunar oxygen, every litre of water extracted from polar ice, every ingot of iron reduced from regolith will represent a victory not just of engineering, but of sustained industrial endurance in an environment built to break industrial systems. The people who eventually achieve this will not be conquering a frontier. They will be maintaining one, day after grinding day, in a place where the environment never relents and the machines never stop wearing down. That is what mining the moon actually means. Not a gold rush, not a land grab, not a shortcut to the solar system. A long, slow, brutally honest confrontation with the fact that the universe does not make its resources easy to claim. And the moon, our closest neighbour, our first stepping stone, is already teaching us that lesson before we have moved a single ton of rock